Before my talk, I will share some information of our university. Our university is Suzhou University, located in the city of Suzhou in the mainland of China. It has more than 100 years history, and where you can see this is the original door of the campus, as well as the door of building and convention center and the Department of Mathematics, as well as the old style gym. We also have a 500 years building with the name of Wenxingde. It starts from Ming Dynasty. Our university has more than 50,000 students and more than 5,000 faculty and staff. From this table, we can find our university in the mainland of China is ranking from 13 to 30, depending on the criteria we provided. And for the natural science, we can find our university develops very rapidly in these years. From the nature index,
你是校长吗？
we just tell you some information. Our nature index has ranking top 10 in the mainland of China. Okay, this is the outline of our my talk today. First, I will show a brief introduction of emergent phenomena in transition metal oxides and their heterointerface. And I will introduce our recent works, including the spin polarized two-dimensional electron gas in the magnetite natrium aluminum heterointerface. And also, I will move to introduce you the two-dimensional whole gas in the Euro-titanium oxide interface. And I also show the ultra-thin chromium dioxide as a quantum anodes Hall insulator. Finally, I will show our calculation on the bulk system, including the high pressure physics of magnetite, as well as the photovoltaic properties of multi-phase chromium calcium ion chromium oxide.
要不要挂在那边比较均匀一点，不然挂高一点。
Okay. So since the discovery of high temperature superconductivity, transition metal oxides has attracted intense interest in condensed metal physics. In fact, in the past 30 years, scientists have witnessed the many emergent fields in transition involving transition metal oxides, including the high temperature superconductor, as well as ferroelectric oxide, and later the gross magnetoresistive magnetites, as well as the recent interest in multiferroism. Scientists usually contrast transition metal oxides with conventional semiconductors. In these two kinds of materials, both the degrees of freedom of charge and the spin plays a critical role, which is also the fundamental of electronics and spintronics. But for the transition metal oxides, we can see the orbital degrees of freedom plays a very important role. It is not only due to the anisotropic anisotropic orbital shift of these d electrons, but also the multiple valence state as well as its orbital occupation depends strongly on the crystal structure and coupled in turn the spin degrees of freedom as well as the electronic properties. This figure demonstrates the orbital degrees of freedom with the so-called charge orbital orbit observed in the magnetites. However, in these transition metal oxides, there's many defects. So the physics behind this field is a little complex. The situation is changed until 2004, where scientists can make atomic control of the growth of this transition metal oxides. The most important finding is the observation of a two-dimensional electron gas at the two-insulator interface. So this system provides a very interesting platform to study not only the control of properties, but also some emerging phenomena. This picture shows a very famous expert who is expert in the spintronics, through Paki, very excited for the observation of conductivity at the interface of the two insulators. And in fact, his group moved to this exciting field. Depending on the growth control situation, it is not strange to argue that for the observed two-dimensional electron gas, the two insulators interface has the origin of, for example, oxygen vacancy and calcium intermixing. But the observation of critical thickness for the appearance of two-dimensional electron gas has provided this picture that is charge transfer by polar controsity plays a critical role. In fact, this is a picture of polar controsity, which describes the polar discontinuity at the interface of two insulators. When we deposit this polar material in a non-polar material, we can find that there is a polar discontinuity develops along the perpendicular direction of this film film. The polymer, as the increase of the thickness of polar material, we can find the electrostatic potential associated with the electrodipole in this polar material will diverges. So, of course, this situation is not a stable situation. Therefore, to overcome the electrostatic divergence we need electronic reconstruction. And in this N-type, there is electron doubler case. We can find the valence state in the strontium titanium first layer. The valence state of the titanium will change from project state to the non-integer state. Therefore, there's a partially occupied electronic state of this previously insulating layers. So there forms a conducting layer as the interface. The same situation is found for the p-type, that is whole doubler case. But for the whole doubler case, we can find it is harder to change the valence state of oxygen. So this whole state, this holes will be compensated by the appearance of oxygen vacancy. Therefore, for the p-type interface, the system is still insulating, but with the appearance of oxygen vacancy. So this picture gives explanation why there appear two-dimensional electron gas or conducting state at the interface of two insulating materials. Besides the conductivities, scientists also observed the magnetism of this two-dimensional electron system. We use the so-called magnetoresistance, spin torque, scanning speed, as well as enormous power measurement and FMM to measure the magnetic properties of the system. Theoretically, depending on the orbital occupation, we can distinguish two types of exchange interaction. Between the same orbital, we can find the magnetic exchange interaction is antiferromagnetic. between the different type of orbitals, the magnetic change interaction is ferromagnetic. So depending on the density of the heterointer electron density, as well as the localized orbital magnetic moment, we can tune the magnetic ordering of this system from condor screened system to the double exchange ferromagnetic system. For our theoretical first principle studies, what can we do? For this system, using first principle density functional approach, we can study the charge distribution at the interface. We can find from this plot, we can find the two-dimensional electron gas has a region of several nanometers. We can also study the orbital occupation of this two-dimensional electron system, where we can find at the interface it is mainly from the dxy orbital. At the inner part, there's xz and yz orbital occupants. And we can also study the Fermi surface of this system and tell some important information on the transport as well as possible superconductivity. Since the polar discontinuity is widely observed in transition metal oxides, this tells us very important information. That is, we can choose the A site and the B site ions to introduce various kinds of polar discontinuity, and where we can study the charge transfer and its consequence on the magnetic order and electronic reconstruction. So our first work is starting from here. We just replace former experimentally observed STO with magnetic perovskite. The first example is strontium manganese oxide, which is a parent compound of the grosso-magnetoresistive manganites. This cubic perovskite has a quadrivalent manganese, which contains 3 localized T2G electrons. And these T2G electrons coupled antiferromagnetic magnetic in the bulk form, and it is insulator. Therefore, we can ask if there is a charge transfer from polar material at an interface. Therefore, we can realize 3 plus ND electron system. And we will ask ourselves, what is the consequence of the electronic structure, metal or insulator, G-type interferromagnetic or ferromagnetic or others? So we construct 3 types of superlattice, which is called N-type superlattice, containing merely N-type heterointerface. We also construct a P-type superlattice, and also as well as NP-type superlattice, which consists of both N-type and P-type heterointerface. The result is here. We can find in the N-type superlattice, the system transformed from previously antiferromagnetic order to the ferromagnetic one. And for the P-type, the system is still the antiferromagnetic coupling. The explanation is very simple. Since the formal empty DG orbital at magnetites is now partially occupied, so this intermediate electrons will mediate double exchange ferromagnetic coupling between previously localized 3D magnetic moment. So the ferromagnetic ordering develops. For the P-type, the holes reside mainly in the oxygen P state. So there's no change of the exchange interactions. So the system is still antiferromagnetic type. The interesting phenomenon is the non-uniform carrier doping in the NP-type superlattice. For the system consisting of both N-type and P-type interface, we can find the electrostatic potential in the superlattice is zigzag line. So there's charge transfer as long as the thickness of this polar layer is thick enough and making the charge transfer to the at the n-type interface. But it is obviously the electron will localize at the n-type interface, while the host is located at the p-type interface. So there's a non-uniform carrier distribution in the superlattice structure, and the consequence is there's non-uniform magnetic ordering developed in this superlattice. And we can find, for example, here, in this case, we can find at the n-type interface, the right-hand side is n-type, and the left-hand side is p-type. At the n-type phase, ferromagnetic ordering is developed, but for the p-type case, p-type interface, it is still anti-ferromagnetic. So we use superlattice structure to realize complex magnetic ordering in this system. After this work, we have realized spin polarized two-dimensional electron gas in this heterostructure. We will ask ourselves, is there spin polarized two-dimensional cold gas? But unfortunately, for this system, the valence state band is composed mainly by the oxygen 2p state. As I mentioned above, the host located as the oxygens will not stable. It will be compensated by the appearance, the existence of the oxygen vacancy. So we should change our strategy. So we should change from this so-called charge transfer insulator to the mod-Hubbard insulator, or change the so-called magnetic valence band in this AbO3 polar scar material. And we have found a very suitable material, that is Euro-titanium oxide. In this system, we have realized the charge transfer induced two-dimensional whole gas, which is also spin polarized. For the Euro-titanium oxide, it has similar structure with the STO as well as the SMO. The A site is composed of Euro, which has 7 localized 4F electrons. And in the bulk form, it is antiferromagnetic and paraelectric. Pioneering theoretical work by Rabi and Philip, they have shown if there is a epitaxial stream imposed, the system will change from antiferromagnetic paraelectric to the ferromagnetic ferroelectric. And their predictions can be realized several years later experimentally, where scientists grows the ETO with different substrate and realized the ferromagnetic and ferroelectric simultaneously. Here we by designing or by introducing superlattice structure, we have realized charge transfer induced antiferromagnetic to ferromagnetic transition. The first case is the N-type superlattice, where the system is regarded as electron doped. We can find a formally band gap located here. The conduction band is partially occupied, and the system is also spin polarized. And the two-dimensional electron gas, or the conductivity state, is composed mainly from the titanium D3D electronic state. And for the p-type state, we also find antiferromagnetic to ferromagnetic transition. But here, the holes is mainly reside at the Euro electronic state. And we can find the system is fully spin polarized. That is, there's a band gap for the downspin channel, and for the upspin, the system is metallic. So we have realized fully spin polarized two-dimensional whole gas in this superlattice structure. This picture shows the emergent of ferromagnetism in this system. The fully antiferromagnetic coupled 4F localized moment becomes ferromagnetic coupled in both N-type and P-type superlattice. But an interesting system is the NP-type superlattice, where we can find as the increase of the polar layer, the band gap, that is the shaded area, become diminished. And we can find in this case, it become a semiconductor. But unlike conventional semiconductor, both the electron pocket and the hole pocket in this case is fully spin polarized. So this provides a very useful picture where both the electron and the holes located at the two sides of the interface is fully spin polarized. And also is unlike reverse extron picture in conventional semiconductor. It is not easy for the electron to jump to the whole band. That is, this extron state is very stable. Regarding recent theoretical paper, if the electron and hole spin polarized with the same spin direction, we will have the chance to become the so-called spin superconductor. That is, at a low temperature, if such condensation happens, the spin transport will displaceless. So using superlattice structure of transition metal oxide, we have also realized the displaceless transport of the spin current. The third example is the so-called half-metallic chromium dioxide. Unlike previously mentioned insulating system, for the transition metal oxide, this is a very rare example. That is metallic. This is a half-metallic, which means in this material, the carrier is fully spin polarized. This material has a very simple crystal structure. It has a rutile crystal structure. And the chromium ion has two electrons. One is localized, the so-called DX1, and another is partially occupied, YZ plus ZX or YZ minus ZX, depending on the crystal site of the chromium. So this partially occupied as well as the localized, fully occupied state provide a double exchange picture that is the origin of the so-called half-metallic electronic structure. The reason why I was interested in this material starts from my postgraduate study in Professor Go's group. Since at that time, we and his experimental collaborators have provided very useful study in these materials. So what we do is to study its quantum confinement effect in this metallic oxide. Generally speaking, for a metallic system, when the dimension is reduced, it will undergo a transition from semiconductor, transition from a metallic to a semiconductor. This is also the observation in this metallic oxide, chromium dioxide. But interestingly, in the critical thickness, we have found a very particular kind of band structure. And for this material, we have studied two kinds of ultra-thin system. That is a superlattice structure as well as a thin film structure. In both cases, we find the so-called Dirac cone electronic structure at the Fermi level in both superlattice structure as well as thin film structure. And interestingly, this Dirac cone is a single spin, that is fully spin polarized. We have also included the spin orbital coupling in this system. and found there's a gap open at the GR cone. So this verifies the system is a chain-use insulator that is a non-topological non-trivial system. We also calculated the Chern number, and the Chern number is 2. And this system provides very example to realize the so-called quantum enormous Hall insulating. And we can find the band gap of the system is 3.7 milli-eV. This is much larger than the experimentally observed chromi-doped topological insulator. And at that case, the band gap or the transition temperature is extremely low. So this example provides a very interesting case to realize topological non-trivial physics in transition metal oxides. Another interesting material is magnetite. The reason is similar for chromium dioxide. Since when I was a postdoc in National Taiwan University, Professor Guo and his collaborator has made a very important finding, that is the charge orbital ordering and the Berry transition. For the first time, they have explained the Berry transition as a consequence of the charge orbital ordering. And later, experimentally, they have observed such kind of charge orbital ordering. What we have done is we studied the high pressure physics of this magnetite. As we know, magnetite is the oldest known magnetic material in the human history. And there's no doubt at ambient pressure and room temperature, it crystallizes in this inverse spin layer crystal structure. And in fact, this crystal structure can be determined exactly. For the high pressure phase, experimentally have identified two kinds of symmetry. There is the PBCM and the BBMM. However, experimental observation is very confusing. Scientists still argue which in which pressure the system should be the ground state. So we use first principle method to determine the exact phase transition or the crystal transition in this material. There's no doubt we can find below around 30 GPa. The inverse spin layer structure is the ground state. But for the high pressure phase, we can find the energy difference between these two crystal symmetry is very small. But using accurate first principle method, we can distinguish these two phases accurately. We can find the system will transist first to the PBCM phase, and then to the BBMM phase. We also studied the mechanical properties of these two phases and compared with experimental data in this table. We can find for the ambient phase, that is FD3 bar M, that is inverse spin layer system. The calculated Hawk modulus agree with the experimental very well. For the high pressure phase, we can find the K increase rapidly. This is reasonable, since for the high pressure phase, the bulk modulus should be large, and which indicate the system is not easy to be compressed. For the high pressure phase, our calculated K is around 500, and its experimental observable is of the same order. And so we're very confident our